In this video, we consider the Prim's algorithm. Recall that in this algorithm, the set X always forms a tree, and we gradually grow it. At each iteration, we attach a new vertex, which is not currently in the tree, to the current tree by the lightest possible edge. And this is in fact very similar to Dijkstra algorithm. Recall that Dijkstra algorithm finds the shortest path between two nodes by constructing the tree of shortest paths from a given source node. We will now illustrate this on a toy example. Consider the following toy example that we've already seen. We are now going to gradually grow a tree which will eventually become a minimum spanning tree. At each iteration, we are going to select a vertex such that it can be attached to the current tree by the lightest possible edge. To select such a vertex, we will use the priority queue data structure. So initially, we know nothing about the graph, so the cost of attaching each vertex to the current tree is just equal to infinity. So initially, the priority or the cost of attaching each vertex to the current tree is equal to infinity. That is, we show here the priorities of all our vertices in the priority queue data structure that we are going to use. Then we declare some vertex, just randomly picked vertex, as the root of the tree that we are going to grow. Assume that we consider this vertex as the root. Now we can change its priority to be equal to 0. It costs us nothing to attach this vertex to the current tree. It is the root. Now we need to process all edges going out of this tree, namely going out of this vertex. Namely, we change the priority of this vertex to 1 because we see that there is an edge of cost 1 that attaches this vertex to our current tree. And for this vertex, we change its priority to 8. Okay? Now we have 5 vertices in our priority queue. I mean all the vertices except for the root, and the cost of one of them is equal to 1, or the priority. The priority of the second one is equal to 8, and the priority of the remaining 3 vertices are equal to plus infinity. So we select the vertex with the smallest priority. This is 1. So we attach it to our current tree. So our current tree looks as follows. Now we need to process all the edges that go out of this tree. Namely, when we add a new vertex, we need to check whether new vertices can be attached to this vertex. When we see this, first we see that there is an edge of weight 6, so we need to change the priority of this vertex to 6. Because it now can be attached to the current tree by the edge of weight 6. Also, we change the priority of this vertex to 9. Okay? Now we have 4 vertices in our priority queue data structure, and we select the vertex with the minimum priority, which is 6. Which is vertex with priority 6. So now this vertex is also in our tree, which is joined by this edge to our current tree. Now we need to process all the edges going out of this vertex to vertices that are not currently in our tree. When processing the edges, we change the priority of this vertex to 4, and we change the priority of this vertex to 5. Namely, we just found a cheaper way of connecting this vertex to our current tree. Okay, now we have 3 vertices in our priority queue. So we select, we extract the minimum value. This gives us the following vertex. So we include it in our tree, which gives us and attach it by this node. Then we need to process all the edges going out of this vertex to vertices that are currently not in the tree. We see that we need to change the the priority of this vertex to 1 because there is an edge of weight 1 that connects this vertex to the vertex which is currently in the tree, and we need to change this priority to 2. Right? Okay, great. Now we have 2 vertices in our priority queue, one of priority 1 and one of priority 2. So we select this vertex. Now it is in our tree and it is connected by this edge, right? When processing all the edges going out of this vertex, we see that there is an edge of weight 3. However, it doesn't decrease the cost of attaching the remaining vertex to the tree, so we keep the priority of this vertex unchanged. So at the last step, we extract the only remaining vertex, which is this one, and we see that the cost of attaching this vertex to the current tree is equal to 2. And this is done by this edge. So now let's compute the total weight of the resulting tree. It is 2 plus 1 plus 4, which gives us 7, plus 6, which is 13, plus 1. So this gives us the tree of total weight 14. We now provide the full pseudocode of the Prim's algorithm. As we've discussed before, it is very similar to Dijkstra algorithm. So once again, the Prim's algorithm gradually grows the tree, which eventually turns into a minimum spanning tree. We use the priority queue data structure to keep for each vertex the minimum cost of attaching it to the current tree. At each iteration, we use priority queue to quickly find the vertex which can be attached to the current vertex by the lightest edge. So specifically, we do the following. Initially, we have, for each vertex, we do not know the cost of attaching it to the current tree, so we just put infinity into the array cost. We also going to keep array parent, which will actually define as a tree. Okay. Initially, we do not, for each vertex of our graph, we do not know its parent. Then we select any vertex of our graph, u0, and we declare this vertex as the root of the tree which we are going to grow. We then update cost of u0 to be equal to 0. So we say that attaching this node to this vertex to the current tree is the cost of attaching this node is equal to 0 because it is already in our tree. We then create a priority queue. So at this point, and we use costs as priorities. At this point, all the vertices lie in priority queue, and the priorities of all of them except for u0 are equal to infinity, to plus infinity, while the priority of u0 is equal to 0. Okay? Then we do the following. At each iteration, we extract the vertex with the minimal priority out of our tree. This means out of our priority queue. This means that we're actually attaching this vertex to the current tree. When we do this, we also need to go through all the neighbors of the vertex v and to check whether the edge that leads from v to this neighbor of v has actually cost less than the current cost or than the current priority of this neighbor. Specifically, we do the following. When we add the vertex v to our current tree, we iterate through all its neighbors. This is done in this for loop. So we iterate through all neighbors z of the vertex v, and we check if z is still in priority queue, namely if z is not in our current tree, and if the current cost of z is greater than the weight of the edge from v to z, then this means that we've just found a cheaper way to attach the vertex z to the current tree, right? And in this case, we just update the value of cost at z. So we assign cost at z to be equal to the weight of the edge vz, and we also say that in this case, if we attach the vertex v to to the current tree, then this will be done through the edge VZ, which means that that V is going to be the parent of Z. Finally, we notify our priority queue that we need to change the priority of the vertex Z to the updated value cost of Z. Since the Prim's algorithm is very similar to Dijkstra's algorithm, its running time is also similar. So essentially what we're doing here is the following. We make V calls to extract mean procedure, right? And also we make at most E calls to change priority method, right? And the total running time depends on the implementation of the priority queue data structure. If we just use array to store all priorities and at each iteration, this means that change in priority is very cheap because we just change the corresponding value in our array. However, for finding the minimum value, we need to scan the whole array. In this case, we get V squared upper bound on the running time. Why is that? Well, once again, because extract mean in this case has running time big O of V. So this is V times big O of V, while change priority has running time big O of 1. Right? It is a constant time operation. Since the number of edges in the graph is at most V squared, this gives us big O of V squared. If, on the other hand, we implement our priority queue data structure as a binary heap, then both these operations have running time big O of log V. In this case, we have the following running time: V plus E times log V. And since in our case, again, the graph is connected, E is at least V minus 1. So this allows us to rewrite the whole expression as big O of E times log V. So once again, the running time depends on implementation. If we use array to implement our priority queue, this gives us V squared. If we use a binary heap, this gives us E log V. Which one is better depends on whether our graph is dense or not. We are now ready to summarize. In this module, we consider two greedy algorithms for the minimum spanning tree problem. The first one is duety-Kruskal, and it uses the following idea. At each iteration, we add the next slightest edge to our current solution if this edge doesn't produce a cycle. To check whether the current edge produces a cycle or not, we use the disjoint sets data structure. Namely, for the current edge UV, we just check whether U and V belong to the same connected component. If they do, we just skip the current edge. The next algorithm is due to Prim. It uses a slightly different but still greedy strategy. Namely, we greedily grow a tree. At each iteration, we attach a new vertex to the current tree by a lightest possible edge. To find such a vertex quickly, we use the priority queue data structure.